that entire star system is being torn apart.
This ain't no game, man.
Indeed, that entire star system is being torn apart, and this isn't in a game. In particular, I've set this amazing new application, SpaceSim, to demonstrate what would happen should a red giant star approach a small singularity too closely. And, predictably, when the red giant got too close, it was pulled apart, shredded by the black hole's gravity. You're watching that happen here in this simulation. This is a brand new simulator that was just released on Steam just a couple days ago at the time of this recording. I've had my eye on this particular simulator for a while because, unlike some previous applications that attempt this sort of thing, this simulator aims for a very high degree of physical realism. It accomplishes this by simulating astronomical objects as particles, anywhere from thousands to millions of particles, and attributing those particles with known physical qualities such as friction, gravity, and heat. Then, we can set those astronomical objects in certain situations and observe the outcomes of their interaction. For example, in this simulation here, you saw that the red giant was shredded by gravitational interaction with the black hole. The black hole's gravity then drew that matter into an elliptical orbit around it, and friction is now acting on that mostly gaseous matter, creating heat that causes it to light up. Friction is also slowing down the orbits of the matter, and bit by bit, the innermost parts of the orbits are approaching the black hole. When some of the matter gets very close to the event horizon, that matter will approach relativistic speeds and be shredded into pure energy. Magnetic fields are simulated in that interaction and will cause jets of energy to fountain from the polar sides of the black hole. Or, more accurately, at roughly 90 degrees to the plane of the accretion disk. So far, the video you have been watching has simulated the passage of about 12 hours very quickly. As we move into the 13th hour, we'll begin to see some of that matter approach the event horizon and be shredded into pure energy. Should happen in just a second. Just there, you saw the first bit of matter approach the event horizon, be shredded, and burst away, driven in opposite directions by the magnetic field. And were we to continue the simulation, as the matter slowed down more and more, we would see those jets last longer and longer. What you're seeing right here is not the SpaceSim application itself, but a video that was rendered by SpaceSim. It's very useful that it can create videos of its simulations because the simulator can be set to operate with only a few particles in light physics, or hundreds of thousands or even millions of particles depending on your computer's power. With intensely accurate physics, and in the latter case, simulations can take quite some time to process, even with a very powerful computer. But you can set it to process a simulation, then render it into a video, allowing you to come back and watch the simulation play out smoothly later on. Let's take a look at the application itself. Before we go any further, I want to take a moment to note that the developer, who I believe is just an individual, named Pavel Sevicek, sent me a key for the simulator. However, I approached him. You see, I've had my eye on this sim as it's been in development for quite some time, and it was about a week or so till it was going to be released on Steam, and I approached him and asked if he would mind if I sent him a few questions. I wanted to do a little interview, just get his thoughts on why he developed the sim, his goal, how much realism he was aiming for, and his thoughts on the potential of the sim, regarding both his thoughts on how far he intended to take the development, and as well as his thoughts on its potential as an educational tool and even a research tool. He replied and said that he'd be happy to do the interview and sent me a key for the simulator. So I did receive it complimentarily. For what this simulator is, it's actually very affordable. It's under $20 USD on Steam. And to be honest, I would have bought it anyway. This simulator is incredible if you're interested in this kind of thing. I mean, I don't know of anything else like this, at least not in the way of software with this degree of accuracy that's designed for anyone to use. I would love to have had access to an application like this back in my university days. The initial presentation of the desktop is deceptively simple. You get your virtual space, you can move around it in 3D, and it's where your simulations will take place. In the lower left, you have a navigation tool. You can grab those round bulbs to move up or down, side to side, or backward and forward. At the top of the upper left, you have 5 drop-down menus. each of which offer many options for fine-tuning the simulator. And center right, you have 3 axis tabs to take the tuning even further. And down the upper left, you have several control icons. When you create a simulation, you hit the gear icon to get access to panels on the right, which allow you to finally adjust the physics to be used and the properties of every object in the simulation. We'll take a look at that in a moment. The simulator is deceptively sophisticated, despite the apparent simplicity of the opening screen. But with that said, once you get used to it, the layout is logical and will allow you to develop an elegant workflow when designing simulations. But to help you get started, the simulator starts out with dozens of interesting presets that you can take a look at. Let's open the menu and take a look at a few now. The first one illustrates the red giant being shredded into an accretion disk by the black hole. And below it, you can see that there are dozens. Some of them aren't even astronomical objects. For example, one simulation illustrates how objects move about as they float on bodies of water. In fact, what SpaceSim can simulate is very flexible and limited only by the imagination. Well, maybe not that much imagination, but it can simulate the interactions between an extraordinary range of objects, such as solids and liquids in ocean settings, planets, stars, black holes and nebulae in deep space, and even the interaction of matter across cosmic distances. Which brings us to the next condition we're going to have SpaceSim simulate. Let's go all the way back to the dawn of the cosmos, when the universe itself may have been a relatively uniform space filled with gas. And from a perspective spanning millions of light years, across billions of years, let's watch how that gas collapses into galaxies, galaxy groups, and intergalactic structures. But before you run a simulation, you should be aware that the more particles you run, the more accurate the simulation is going to be, and the more interesting it will be to view. But every particle has physical properties and interacts with every other particle, which eats up memory and computing power. So before you begin anything, you should have SpaceSim run a benchmark and determine what your computer's capabilities are. From what I've read, SpaceSim considers the ability to run 20 to 30,000 particles pretty powerful, and the preset simulations seem to default to those values. Let me take a moment and see what my computer is capable of running. To do this, I'm going to go to the drop-down menu and select Tools, and then run Benchmark. SpaceSim will run a benchmark on the capabilities of processing by way of your CPU, and then another benchmark on the capabilities of processing by way of your GPU. When you run the benchmark, it'll run this little simulation, showing 3 planets in decaying orbits around a black hole. The first planet is quickly drawn too close to the black hole where it is shredded and begins to form an accretion disk, while outlying particles of that planet form a queue which smash into and interact with the other planets, slowing them down and eventually drawing them into the destructive accretion disk. It will run this first on your CPU and then your GPU. As a point of interest, it's amazing how fast the Mars-like planet is destroyed by the accretion disk. It doesn't even survive first contact with it, revealing the incredible power of those disks. They're like cosmic circular saw blades. But after quickly running the simulation, SpaceSim presents you your benchmark. With my computer running the CPU, I can run 116,000 particles at real time. And if I run the simulation on the GPU, I can run 186,000 particles in real time. Note that the developer is still working on making the GPUs fully compatible with SpaceSim, and at times trying to run a simulation on the GPU can be a bit buggy, though I'll add that I haven't yet experienced any bugs using a modern GeForce video card. I'm going to go back to the presets menu, scroll down the list, and this time find galaxy formation. There it is. Let's click on it and read the description of this simulation. According to the description, the simulation starts shortly after the Big Bang, when space is uniformly filled with matter. As the universe expands, we see the emergence of structures and formations of galaxies. The presets show a small cube-shaped region of the universe, simulated using periodic boundary conditions. We'll go ahead and click OK, and SpaceSim will set up to run it. At the outset, SpaceSim presents us with a cube, where roughly uniform matter in the form of hydrogen gas is contained. Taking advantage of my computer's substantial processing power, I'm going to click and drag on the particle count box and set the particles for 125,000. Ripples begin to be introduced into these primordial gases due to gravitational interactions as they move about. With the simulation actually chosen, off on the right we can see and set simulation parameters. We could make further adjustments to the particle count, including particle limits per body and max particles emitted, as well as the physical parameters we want the simulation to consider, such as hydrodynamics, gravity, cohesion, phase changes, stellar heating, stellar evolution, stellar wind, and so on. In fact, there is so much ability to customize and adjust the depth of any simulation that in this introductory video, we just barely have time to introduce the concepts. Going into the full capacity and scope of SpaceSim would be a project for many videos, and if you're interested, let me know, we'll do just that. I believe in SpaceSim. This is an amazing educational and research tool, and if nothing else, it's simply fascinating in that you can set up these remarkable simulations and watch them play out with the particles' actual physical characteristics and interactions accurately modeled. In addition to having set the simulator to run 125,000 particles, I set the physics to moderately realistic. I could set them to very close to fully realistic in so much as can be simulated, but that would considerably slow down the simulation time. That's a thing to do and then have it record to video and watch later. You can set how quickly simulated time passes and the amount of time that passes per unit, such as 10 seconds per second or 10 years per second, to control the temporal depth and accuracy of the simulation, and you can monitor how much simulated time has passed up here. In the simulation, we can see that interactions between gravitational sources, such as black holes, and the movement and mass around the simulation is beginning to set up waves and ripples, which are causing the gas clouds, mostly hydrogen at this point, to interact and begin to collapse. This will lead soon to the formation of the first stars and the first galaxies. It's about to get interesting in there, so let's zoom in and take a closer look. In the graphs to the lower right, we get readouts on momentum, angular momentum, and kinetic energy currently simulated within the sim, graphically illustrating the cosmic powers operating within the space of the simulator. And you may notice the first dim red beginning to appear now. Clouds of gas orbiting early supermassive black holes are beginning to coalesce, heat up, and light up, forming the first galaxies. I've skipped the preceding several minutes of the simulation, which accounts for roughly the 2 billion years after creation to about 1 billion years ago, and I'm going to have the simulation run to what we estimate to be the present. And you can see at this point that the gases have coalesced into galaxies, which themselves have coalesced into clusters and superclusters of galaxies, and substantial voids have developed between areas of mass. I'm going to show you now just how easy it is to turn such a simulation into a video. As SpaceSim works, it saves the crunched information. You can then go to the double vertical line icon that looks like a pause icon and click on it. The icons will change to 2 arrows in a loop in a circle with a red dot. If you click on that, it'll replay the entire simulation and render it to video. Or you can click on the right triangle, that's the play icon, in which case the simulation will simply carry forward without recording. If you click on the play icon with the red dot, the simulation will continue to play and carry forward while recording and rendering. Or you can click on the loop beside that and the sim will start over again without recording. I'll click the loop with the red dot for it to replay the entire simulation to this point. Because much of the information has already been processed, the creation of the video goes quite quickly. SpaceSim will first replay the simulation, recording it as it goes along, and then automatically render the recording. When it's done, just pick the name of the newly recorded file and where you want it saved. You can go back and replay the simulation, which will run smoothly. This is great for creating presentations for students, or for putting information together to observe at a later time. I'm just going to replay the video. Bear in mind how amazing this is when you watch it. In the space of about 1 minute and 15 seconds, this video is going to portray over 14 billion years of cosmic evolution, and how the universe evolved from a uniform expansive gas that exploded into light and stars and galaxies and superclusters, nebulae, the filaments between galaxies, and the voids between the cosmic spaces, and everything else. When you consider all of that this simulation is portraying creation coming together and taking form, it is truly dazzling. While the presets are very interesting, they merely show what can be done with SpaceSim. With a little understanding of the simulator and some knowledge of astrophysics, you can set up almost any kind of simulation. SpaceSim comes with a number of default objects you can throw into a simulation to quickly illustrate anything. More is planned by the developer for the simulator, and it's possible to add more. Just for illustration purposes, I'm going to put a neutron star in the middle of the simulator, right about there. I can change any physical characteristic of the neutron star, its diameter, its position, its velocity. In this case, I think I'll just rotate the star a bit, so that the jet points momentarily toward us. Now, I'll set a small planet to orbit around the neutron star. To do this, I'll go to the Planets menu. Mercury is a pretty small planet, I'll pick that one. The gray rings show its diameter though, and notice in diameter it is much bigger than the neutron star. I'll set it one Earth radius that's 1 block away from the neutron star, and then adjust vertical velocity to set it in orbit around the neutron star. The planet starts off without velocity, and a small gray vector indicator indicates that it will move directly toward the neutron star as a result of the neutron star's gravity. But I'll click and drag on the z-axis velocity box, increasing the planet's downward velocity and establish it in a circular close orbit around the neutron star. This simulates how orbital mechanics work. Simulations can be as simple as this, or illustrate much more complex phenomena. Anything is possible, and illustrating how to set up simulations on SpaceSim would be a project for many videos, so we'll come back to the topic of how to set up simulations in a future video. For now, I want to leave you with what I consider to be an extraordinary demonstration of the power of SpaceSim and just what can be accomplished with it. Several years ago, NASA created this video to illustrate what it would be like to approach and enter the Great Orion Nebula. It is a strange, gigantic realm of dust clouds, metallic space bullets moving at near relativistic speeds, ripping stellar winds of unimaginable power, new, young, hot stars, and to me, most interesting of all, proplyds, better known as protoplanetary disks, places where matter in the form of heavier elements, rocky materials, and heavier gases have accreted into disks which are themselves collapsing into planets, asteroids, comets, atmospheres, and all the other amazing things we find in star systems. We're just now passing one on the right, and there's another one ahead just on the left. The bubble around the protoplanetary disk is created by the young star's stellar wind, pushing back against the force of the wind given off by the many other stars of the Great Orion Nebula. And within, we can see the dark expanse of a disk rotating around a central star. Interactions of the materials within this disk will ultimately create ripples, which will eventually lead the material to collapse into the various planets that will comprise the star system. The Hubble telescope has photographed some of these protoplanetary disks, and the image on the lower right is very similar to the one that you saw in NASA's animation. Within the protective bubble created by the solar wind of the nascent star at the center, a small, dark accretion disk is coming together around the star, and, given time, millions of years, it will eventually collapse into the planets of a star system. And I've used SpaceSim to set up and illustrate this process. This is a rendered video that I've created with SpaceSim, having it use the power of my computer's GPU to create a simulation in which 1 million particles orbit in the form of a protoplanetary disk using full physics around a central star. These particles will be allowed to interact with one another by way of gravity and random collisions and lead to their collapse. This leads to setting up ripples within the protoplanetary disk, resulting in the formation of early protoplanets. You can see some just now forming at the edge of the protoplanetary disk, with velocity vectors to mark their positions. In the outer, less energetic regions of the protoplanetary disk, fairly quickly, and by quickly I mean over millions of years, hundreds of protoplanets begin to develop. And further into the disk, you can see visible collapse of the dust into ripples. As the protoplanets grow, their increasing gravity will begin to alter their orbits and lead to planetary collisions. setting up more ripples within the disk and leading to the collapse of more particles into young planets. Notice that the matter at the very center of the disk is beginning to glow hotter and hotter too. This is because the increasing number of protoplanets creates gravitational interactions that cause some of the particles to slow down, and they fall toward the center, accelerating as they go, leading to more collisions, setting up more kinetic energy, and creating a great deal of heat around the central star. Even using my computer's powerful GPU, it took 3.5 hours to create this simulation due to the number of particles and the implementation of fully accurate physics. And the full simulation runs for about 20 minutes, so I'm not going to run the whole thing here. I just wanted to illustrate to you the power of the simulator, just how accurate and amazing it can be. On the screen, you'll see some of those young protoplanets are beginning to glow as their increasing gravity is pulling particles, which represents asteroids, into them faster and faster, leading to powerful asteroid impacts that heat their surfaces. They are also beginning to tug more and more on one another, leading to planetary collisions. Lower left and progressing rapidly right, you can see another planetary collision happening, all while another protoplanet is drawn into the collision. Just as in real life, unexpected things can and often do happen, and that's because this isn't an animation, this is a simulation. As more of the hundreds of early protoplanets collide and become new worlds, I noticed that the orbits seem to be slowly stretching out toward the right, and could not make sense of what was leading to it. Right now, we are watching protoplanetary interactions, I would say about as far out as Uranus or perhaps Jupiter. So I paused the simulation and pulled way back to see what was going on. Having backed out to an extreme distance, giving a perspective of the young star system from about the distance of, say, the Oort cloud to our own sun, I discovered that a large area of mass had been gathering behind my perspective, and it looks like a supergiant planet is forming on the outer regions, its significant gravity already drawing a lot of mass out that way. And the fact that it's there represents something that I really truly love about SpaceSim. It doesn't just animate conditions, it simulates physics, including the chaos those physics can create. After all, that gigantic planet that's forming out there is not something that I programmed into the simulation. It was entirely unanticipated, and it happened due to the interactions of the physics within the system. Back in the main region of the simulation, near the star, and after millions of years of simulated time, most of the particles, representing clumps of gas and asteroids, have collapsed into planets. Though I wouldn't call them stable yet, there are still many interactions to be had. Some planets will be destroyed, pulled apart by the very energies that created them, while others will collide and yet form new planets. And as you can see, they're all very hot right now, heated by the poundings of countless asteroids ramming into them and being turned inside out by planetary collisions and powerful gravitational interactions with other planets that have orbits that are not yet stable. This is the amazing power of SpaceSim, to simulate the physics of astronomical phenomena to a degree that was, up until recently, pretty much specifically the realm of astrophysicists. And if you're interested in this sort of thing, it is an amazing tool. I can't speak highly enough about it. Now, for those of you who've watched the Sky Story channel for a while, you know that I avoid doing product reviews. I don't want the Sky Story channel to be one of those channels that feels like it's always just trying to sell you something. But I will certainly let you know if I have encountered something that I think is truly valuable to the astrophotography and astronomy community. And as you can probably tell, I really like SpaceSim. I think that not only is it fascinating, but it has tremendous potential as an educational and research tool. And at under $20 USD, you can hardly argue with the price. There is just so much potential in SpaceSim. And in the next video, I hope to have some feedback from the developer himself about the future of SpaceSim. Thanks for watching. Now get out there and shoot the sky, or maybe just simulate it.